So think about any object that's moving up and down over and over again. So this animation here is an example of a washing machine that's moving over and over. What's happening there? We're putting energy into the washing machine so it starts to vibrate. And it's going to vibrate, and the key word here is periodically. So it's doing it over and over again in a consistent way. When we talk about the idea of a wave, just in general, it's a means of transferring energy via disturbances caused by vibrations. So if we look here at this animation we've got here to the left, what it is, it's a cup that's being vibrated. And we can see the ripples are occurring over and over again. The ripples almost seem stationary in this animation. Now we could talk about all sorts of waves, but for this unit, we're going to focus specifically on sound waves. Now, what makes a sound wave unique? Well, our ears can pick up on it. So if something's vibrating at just the right frequency, our brains interpret this as notes. So for example, if something vibrates up and down 440 times, we call that an A note. If something doesn't vibrate often enough, we can't hear it. Or if something vibrates too often, we can't hear it. There's a very specific range where we can hear things. Now, all of our hearing in everyday lives are tied down to how the wave is created. So there's two factors we have to look at. We have to look at the direction of the motion, so where the particles are actually going, and the direction of the wave. So our sound is made up of basically two ideas. One is going to be the first idea is a transverse wave. So it's when the direction of motion and the direction of travel are perpendicular. So you can think of a wave being like this with my hand. So it's moving up and down in this case. Okay? So in this particular case, what's the energy doing? Well, the energy is going up and down because that's how my hand is moving. Now, if I have my face in front of me, what I can see is that the wind is coming towards me. So the energy disturbance and the way it's traveling are perpendicular. That's the idea of a transverse wave. So if we think of an example of, let's say, a guitar would be an example of a transverse wave. Why is that? Because remember, I'm plucking up and down, so the energy can go back and forth along the string. So I pluck, and it goes back and forth. Now, how you're able to hear things, though, is an example of a longitudinal wave. And this is an example where the energy I'm putting in is parallel. So you can think of this example like a speaker. A speaker is going to move in and out. So instead of the energy being up and down, it's going to go in and out. And if I have my face in front of me, I can see that wind is being pushed towards my face. So the direction of motion and the direction of travel are parallel in this case. Now, when two waves come together and they're going to compress like that, we call that compression. The opposite of compression, where the waves are more stretched out, we call rarefaction. So here's a good animation, and what this does is shows an example of both waves as a transverse and as a longitudinal. So in both cases, the energy is moving from left to right, but how the disturbance is occurring is different. So this is the point where we're going to label parts of the wave. Now the first idea is the idea of a cycle. Now a cycle is defined as a complete sequence that gets repeated. How you choose to define this is up to you. So for example, I could go from right here. So in that case, the full cycle would be all the way up, all the way back down, and all the way to the center again. I could just as easily define that as being from a crest, all the way down, and all the way back up. That is one complete cycle. Now the period is how long does it take for one complete cycle to occur. When we talk about frequency, frequency is saying how many times does something occur per second. So 1 over seconds, which is hertz. To give you an example of this would be, let's say a complete cycle takes 3 seconds. So the period in this case would be 3 seconds. What would our frequency be? Our frequency would be 1 over 3. So 0.33 1 over seconds. Nobody actually writes it as 1 over seconds. We end up writing this as 0.33 hertz. So another example, let's say it took us to produce an entire wave 0.05 seconds. Our frequency in this case would be 1 over 0.05, which would be 20 hertz. So when we talk about more terminology with a wave, it's talking about the distance of or the idea of a wavelength. So it's the distance between any two adjacent points. So for example, we could be saying from here to here. Or you could do from peak to peak. Now you may be asking yourself, wasn't that a cycle? What's the difference? The difference is when we're talking about cycles, we're talking about the time it takes for a complete wave. When we're talking about wavelength, we're talking about the physical distance, so like in meters, of an entire wave. When we talk about amplitude, it's basically from the max disturbance of the wave from the 0 point. So basically from the middle to the peak. When we talk about the idea of the wave equation looks at two different ideas. It looks at frequency and it looks at wavelength. So I know we've learned earlier this year that speed is equal to distance over time. So how can both things be true? Well, let's think about the units for a second. When we talk about distance, we typically measure distance in meters. And time, we measure in seconds. That's why our units for speed is meters per second. Now we're learning the equation velocity is equal to wavelength times frequency. Now wavelength is the distance of our wave, so we know this is going to be in meters. Now frequencies, we know frequency is hertz, and a hertz is 1 over seconds. So when you multiply meters times 1 over second, you still end up with the units of meters per second. So two key ideas that we're going to have to talk about when we talk about sound. 1. The speed of the wave is dependent on the medium through which it is traveling, not on the frequency or wavelength. So, for example, if you were to have a piece of metal and you were to have air, the sound will travel faster through the metal than it would through the air. 2. The frequency of the wave is determined by the source producing the wave. It doesn't matter whether you have something going through air or you have something going through metal. The frequency is determined entirely by what's actually making that wave. So for our first example here, how far does a 440 Hz wave with a 0.2 meter wavelength travel in 2 seconds? Go ahead and pause the video. Try it out. So I'll assume at this point you've tried it, so we can start to take it up. So now let's take a look right here. We know that our formula here is velocity is equal to wavelength times frequency. So 0.2 times 440. When we put that into our calculator, we end up with 88 meters per second. Now remember, frequency, when we talk about 440 Hertz, that means there's 440 waves being produced every second. So it's like saying 440, 1 over s. So we now have the speed of our object. We also have the time. And we know from the first unit that v is equal to distance over time. So 88 is equal to distance times 2, which means our distance is going to be 176 meters. Now for our next example we're going to talk about, we have this information. And what we're going to try to do is find the wavelength, period, frequency, amplitude, and velocity. Now the key we have right here is that it's recorded in 0.5 seconds. So go ahead and pause the video, try this out, and then we're going to take it up. Okay, at this point we can start to talk about it. So the first thing we want to do is we're going to talk about the peak wavelength. So remember, we're measuring that in meters. So I'm going to take a look at this, and if I'm going to say 3/4 of the wave is about 6 meters, I'm going to estimate that the wavelength here is about 8 meters. Now, period is time. Now, we can see that in 0.5, we had 2 full waves. Then I'd argue the first wave here was produced in 0.5 seconds. So our period is, 0.25 seconds. So the next thing we're going to talk about, and I'll bring up my screen, is frequency. Frequency is equal to 1 over the period. So 1 over 0.25, which means we have a frequency of 4 Hertz. If we go back to our screen for a second, it's asking us for amplitude. So I would look at this right here, and I would say that our amplitude is going to be 4 meters high. The last question it's asking for is velocity. So if we talk about velocity, that's going to be equal to wavelength times frequency, which is going to be 8 times 4, so 32 meters per second. Now that you've seen me go through one example, try this one out, and when you're ready, unpause the video and we'll go through it. So let's take a look at this. If we look at our entire drawing here, we can see that we have 2.5 waves over 1 meter. So now let's go ahead and go through the calculations there. So now let's start to take up the question. We know for our wavelength, we know we had 2.5 waves, and we know the length of the entire 2.5 waves was 0.05 meters, or 5 centimeters. And because we're having to divide this by 2.5 waves, we know that the wavelength will end up being equal to 0.002 meters. The next thing is asking for period. And remember, period is time. So now if we go back to the diagram, we can see that over 1 second, we are producing 2.5 waves, which means our period is equal to 0.4 seconds. Now, frequency is always 1 over period. So this is 1 over 0.4, which is equal to 2.5 hertz. Amplitude. If we take a look at our drawing, because this one's a little bit tricky, so I'll bring it back up, we can see we're starting at 7 and we're ending at 10, which means the amplitude in this case is just going to be equal to 3 centimeters. Last thing we're asking for is velocity, and velocity is equal to wavelength times frequency. So when we plug in 0.002 by 2.5, we're going to get a very small number. We're going to end up with an answer of 0.05 meters per second.